In Lecture 7, we turn to multivariate optimization, that is, optimizing with functions that have more than one exogenous variable. In Module 1, we start by defining multivariate functions. In this course, we'll restrict ourselves to functions of two variables. We'll look at one function in a bit more detail, namely the Cobb-Douglas production function. After that, we'll move on to differentiation of multivariate functions. We'll examine first-order partial derivatives and then second-order partial derivatives. This provides the foundation for optimization we'll discuss in Module 2. Recall that a function is a rule that maps or transforms one or more variables into another value. With a function of two variables, we have an ordered pair, say x and y. These are coordinates on the xy plane. The domain of the function is the set of values of x and y for which the function is defined. Here we have the xy plane, where our domain is values of x greater than 5 and values of y greater than or equal to 10. Here's a function of two variables. So we have f of x and y is equal to 5 times x to the fourth y squared minus 2xy to the fifth. If we're going to plot that, if we're going the values of our x, the values of our two variables are in the xy plane, but the value of the function is in the third dimension, for example. So we'd have the x-axis, the y-axis, and then vertically f of x, y. So our domain for our function is down here, and the values of the function are marked along this vertical axis. We usually let a function of two variables equal z as a common convention. So just to recap, x and y are the independent or exogenous variables. That is the argument of the function. Z is the dependent or endogenous variable. We saw the domain of the function is that ordered pair of values x and y. And then we have the range of the function is the corresponding values of z. Let's look briefly at a function of two variables you'll come across repeatedly in economics. It's the Cobb-Douglas production function. This function was developed and the parameters estimated statistically by two economists, Charles Cobb and Paul Douglas, between 1927 and 1947. Douglas later became a US Senator. So this is the general form of the Cobb-Douglas production function. So we have a function of two variables. It's equal to a, some constant, times x to the lowercase a, y to the lowercase b, and our domain is values of x and y greater than 0. The function was developed to represent the relationship between labour, capital and output in an economy. So originally it was a macroeconomic model. However, it's also used widely in microeconomics, as it has some nice properties, such as diminishing marginal returns for the inputs and convex isoquants. We won't go into those properties in this course. What we will look at is the relationship between inputs and output. So we have our Cobb-Douglas production function in its usual form. So Q, the quantity of output, is a function of capital and labour. K is the amount of capital used. L is the amount of labour. A, the coefficient, represents the level of technology. In economics, we're often interested in how economies grow, or how companies grow. Let's see what happens when we double the quantity of both capital and labour. So originally we had K units of capital and L units of labour. We're increasing those to 2K for capital and 2L for labour, substituting in there. We can simplify that. So we'll have A times 2 to the little a, K to the A, 2 to the B and L to the B. We can collect the 2's. So we have 2 to the A times 2 to the B. Well, of course, that's just 2 to the A plus B. So we have 2 to the A plus B times A times K to the little a, L to the B. Well, that's just Q up there. And so we have Q to the 2K, 2L is equal to 2 to the A plus B times Q to the KL. If we just replace 2 by some arbitrary value t, we We prove the general case here. So what does that mean? Well, we introduce the concept of a homogeneous function. A homogeneous function is one in which if the argument is multiplied by a factor, then its value is multiplied by some power of this factor. So we see for the Cobb-Douglas production function, this factor is a plus b. Now, if a plus b is equal to 1, then the function is homogeneous of degree 1. If that's the case, then the production function exhibits constant returns to scale. For example, as we saw, doubling both the inputs doubles the output. Tripling the inputs will triple the output. Now, constant returns to scale is an assumption that's often made in economics, as it has many useful properties. Not all production functions are homogeneous of degree 1. As I mentioned before, the degree of the homogeneity is a plus b. If a plus b is greater than 1, then the production function exhibits increasing returns to scale. For example, doubling both inputs more than doubles outputs. If we had the case where a plus b is equal to 1.6, we could double the inputs, double both labour and capital. The factor we'd multiply it by would be 2 to the 1.6, and so we'd double inputs and output would increase by 3 times. Many modern industries exhibit this characteristic of increasing returns to scale. For example, the car industry. Japan produces nearly 8 million passenger cars per year. For Germany, it's nearly 6 million. The average cost of production in those countries is much lower than the average cost of producing cars in Australia. This is the main reason Australia no longer has a domestic car industry. We can also have decreasing returns to scale. This is where a plus b is less than 1. So if we double inputs, for example, and a plus b is equal to 0.8, then output increases by 1.74. Decreasing returns to scale can occur when a firm gets too big and too complex to manage effectively. It could happen with some very large conglomerates, companies that produce a wide range of unrelated products. If you're interested in homogeneous functions, you can read more about them in section 12.6 of our textbook. However, it's not a topic we'll go further into in this course. Something to keep in mind though, returns to scale are a long-run property when both labour and capital are variable. Don't confuse it with diminishing marginal returns, for example the marginal return of labour. This is a short-run property where one factor is held constant. In the case of the marginal return to labour, the amount of capital is held constant. So that was just a brief introduction to the Cobb-Douglas production function. We come across it fairly regularly in lectures 7 and 8, so it's good to know a little bit of background to it. Now let's return to the main topic for this module, partial differentiation. So we have a production function. We might be interested in how much output will increase if capital is held constant and labour is increased. In other words, we want to determine the marginal product of labour. The marginal product is the extra output obtained by employing an extra unit of input. We always specify the input, in this case it's labour. The word product refers to output. The word marginal refers to the fact that we're increasing input, say labour, by 1 unit. So as economists say, we're considering changes at the margin. We saw how differentiating functions of one variable tells us about small changes in a function. We could apply the same techniques to multivariate functions with only fairly minor modifications. We consider the change in the function when one variable changes, but, and this is an important but, with all the other variables held constant. In this course, we'll restrict ourselves to functions of 2 variables, but the principles can easily be extended. We have a function z equals 2x cubed plus 4y squared. How does z vary when x changes by a small amount? Well, that's the rate of change of z with respect to x. We differentiate z with respect to x, considering y to be a constant. Instead of having dz dx, we have del z del x, and we just differentiate with respect to x as we would with a univariate function. So we apply the power rule, differentiate 2x cubed is 6x squared. Our second term there, 4y squared, we can consider a constant, so the first derivative with respect to x is 0. Similarly, we can differentiate with respect to y. So that's the rate of change of z with respect to y. That's del z del y. In this case, we're treating y as the variable, and we're holding x constant. So 2x cubed is a constant. The first derivative with respect to y will be 0. We apply the power rule to the second term. That gives us 8y. We can summarise that information. So we have a function, z equals f of xy. Then del z del x is the first partial derivative with respect to x. That is, we're differentiating with respect to x, considering that y is held constant. Similarly, del z del y is the first partial derivative with respect to y. We consider x to be held constant. We have a variety of notation for partial derivatives. We've seen del z del x. We could have del f del x, more completely del f of xy del x. Another form of notation is to use z, so z prime, but we need to indicate which variable we're differentiating with respect to, so we have a subscript. So it'll be z prime x or z prime y. Another form is based on f of xy, so we'll have f prime of xy. Again, the subscript 1 and 2 tells us which variable we're differentiating with respect to. So the 1 and 2 refer to the position of the variable in the argument. So we have the argument there is xy. Of course, x is in position 1, y is in position 2. These two are the forms of notation we'll most commonly use in this course, although the others are perfectly acceptable. We started this discussion of partial derivatives wondering about the marginal product of labour for a given production function. Let's now look at an example of a Cobb-Douglas production function with constant returns to scale. Here we have q is equal to a to the k alpha, l to the 1 minus alpha. That's a slightly different form to what we saw before. We're replacing a and b by alpha and 1 minus alpha. We have constant returns to scale, so our exponents alpha plus beta are equal to 1. Well, that implies that beta is equal to 1 minus alpha. So we replace beta by 1 minus alpha here. We want to determine the marginal product of labour and the marginal product of capital. Let's look at the marginal product of labour first. As I noted earlier, the marginal product of labour is equal to the first partial derivative of q with respect to L. So we'll have del q. It's a function of k and L, del L. We're taking a partial derivative with respect to L, so we're treating k as a constant. A is also a constant, so we can just take a to the k alpha as a constant. So the marginal product of labour will be the constant a to the k alpha. We differentiate the L term using the power rule. So bring the exponent down, that'll be 1 minus alpha times L to the 1 minus alpha minus 1. And so that's equal to 1 minus alpha first, a, k to the alpha, L to the minus alpha. Another way of writing that, we would have 1 minus alpha, a k to the alpha, over L to the alpha. Similarly, for the marginal product of capital, if the marginal product of capital is equal to the first derivative of q with respect to k, so del q, del k. Now we're treating L as a constant, so we'll have a times L to the 1 minus alpha as a constant. And we apply the power rule to differentiating the k term. Bring down the exponent, k to the alpha minus 1. Just rearranging that into the more normal order, we'd have alpha times a, k to the alpha minus 1, and then L to the 1 minus alpha. And there we have the marginal product of labour and the marginal product of capital for our Cobb-Douglas production function. Let's look at another example. Here we have z, a function of x and y. We want to find the first order partial derivatives. We'll start with the derivative with respect to x. That will be del z del x, or we could write that f1 prime of x and y. We're holding y constant and applying the power rule when we see an x. So in our first term there, we'll have what'll be 5 times 4 x to the 4 minus 1 times y squared, a constant, minus, well, 2 times x to the 1 minus 1, y to the 5th Simplifying, we'll have 20 x cubed y squared minus, well, x to the 0 is 1, 2 times y to the 5th. Similarly, differentiating with respect to y, we'll have del z del y equal to f2 prime. This time we're holding x constant and differentiating y. So we'll have 5 times 2, well, x to the 4, y to the 2 minus 1, minus 2, bringing down the 5, so that'll be 5 times x, y to the 5 minus 1. And so simplifying, there we'll have 10 x to the 4, y to the 1, well, that's just y, minus 10 x, y to the 4. So as I mentioned earlier, finding partial derivatives isn't that much different to differentiating univariate functions. There are also higher order derivatives. We'll use second order partial derivatives in optimization problems, just as we use second derivatives in univariate optimization. The second order partial derivatives are a little bit more complicated than the univariate case. We have 4 second order partial derivatives. There are the obvious ones when we differentiate the function twice with respect to x and twice with respect to y. So we would have del f del x and differentiate again with respect to x, and we get del squared f del x squared, and similarly in the case of y. There are also what are known as the mixed partial derivatives or mixed partials. If we take the first partial derivative of the function with respect to x, we can then differentiate it with respect to y. Here we have del f del x, and we can differentiate that function with respect to y, giving us del squared f del y del x. Similarly, if we have del f del y, we can differentiate that with respect to x and get del squared f del x del y. What we'll see as we go through examples is that there's symmetry between the mixed partials, where del squared f del x del y is equal to del squared f del y del x. This will be the case as long as the second order partials are continuous functions. Now let's go back to example 2 and find the second order partials. To find the second order partial derivatives, we start with the first order partials, differentiating del z del x once more with respect to x. We'll have del squared z del x squared, and that will equal 60x squared times y squared minus, well, we just have a constant there in that second term, so that'll be minus 0. So it'll be 60x squared y squared. Differentiating del z del y once more with respect to y, we'll have in our first term 10x to the 4 minus 40x y cubed. Once again, we start with our first partial derivatives. This time we want to differentiate del z del x with respect to y. So we'll have del squared z del x del y is equal to, well, we have 20x cubed minus y squared. This time we're differentiating with respect to y, so we'll have 20x cubed as a constant. We bring down the exponent, 2, so we'll have 40x cubed y to the 1 minus 10y to the 4. The other mixed partial is del squared z del y del x. This time we're differentiating del z del y with respect to x. We'll have 40x cubed times y minus 10 times y to the 4. And we see that's equal to del squared z del x del y. That's normally the case. Here's another example that you can go to now or look at the end of this module. We'll finish Module 1 with an example of how partial derivatives can be used in economics. We've come across demand functions in earlier lectures. There we thought about demand in terms of quantity as a function of a good's own price, or the inverse demand function where we had price as a function of quantity. However, there are many factors that determine the quantity demanded of a good. Income, for example. Other factors are the prices of other goods. If you've done some microeconomics, you'll know that some goods are substitutes. They compete against each other. There are many examples of substitutes: butter and margarine, natural gas and electricity for cooking and hot water, steel and aluminium for manufacturing. If goods A and B are substitutes, and the price of A goes up, demand for A will decrease, and the quantity of B demanded will increase as consumers switch from A to B. Other goods are complements. They're consumed together. For example, game consoles and games, cars and petrol, mobile phones and apps. Say goods C and D are complements. If the price of C increases, demand for C will decrease, but the demand for D will also decrease because C and D are consumed together. Here we have a linear demand function where the quantity of A depends on some constant, then A's own price, the price of some other good B, and income. Here we're leaving the sign of the term B times PB. Indeterminate. It's clear that if the sign is positive, we have substitutes. If the sign is negative, then we have complements. However, the situation isn't always so clear. Hopefully, you will have already thought of how partial derivatives fit into this analysis. If A and B are substitutes, then the partial derivative of quantity A demanded with respect to the price of B is positive. If A and B are complements, then the partial derivative of the quantity demanded of A with respect to the price of B is negative. Of course, if we have a linear demand function like this one, where the sign of the coefficient is clear, the answer is obvious. It's not always so clear. Let's look at an example where that's the case. First, let's get these functions into a more usable form. To determine whether A and B are substitutes or complements, or neither, we really only need to analyse one demand function. Let's look at the demand for A. What are the conditions? If the first derivative of the quantity of A demanded with respect to the price of B is positive, then A and B are substitutes. If the partial derivative of QA with respect to PB is negative, that implies that A and B are complements. So let's find del QA, del PB. We have a demand function for good A. We differentiate that with respect to the price of B. Here's our PB term. We apply the power rule to that. So we'll have 50 times 3 on 2 times PB to the 3 on 2 minus 1. We're treating PA as a constant. So it'll be PA to the minus 1/2. So we'll have 75 times PB to the half, PA to the minus 1/2. Getting it back in the form we originally had, that would be 75 times the square root of PB over the square root of PA. We know that prices are positive. The coefficient 75 is positive. Therefore, we conclude that del QA, del PB is also positive. That implies that A and B are substitutes. I'll leave you to show that we get the same result if we differentiate the demand function for B with respect to the price of A. That concludes Module 1. In Module 2, we'll apply partial differentiation to multivariate optimization.